Hello and welcome to biology. So I will come up with a catchy starting line, but for now that's all I got. Alright, so we just finished setting up and recording the data for potatoes, different potatoes that are placed into various solutions with different molarities. Okay, so I accidentally mislabeled the containers, and so we color-coded them with different food coloring dyes so that we could tell the solutions apart. So now our job then is to use our data and to figure out which solution is the 0 molar solution or distilled water, which one is 0.2, 0.4, 0.6, 0.8, or 1.0 molar solution of sucrose. Alright, so here's some sample data. This is potato core data. It is not the stuff that you recorded, however, it is representative of kind of what you might see. Again, the colors do not correspond with what your change of mass will end up being, but you should be able to get the idea and apply it to your actual information. Okay, here we go. So, the first thing that we have to do, because we started with potato masses of all different types of starting masses, is that we have to kind of even the playing field, and so we will calculate something that is called the percent change in mass. And we do that by using the following formula here, where we take the percent change of mass is equal to the mass, the final mass, minus the initial mass, divided by the initial mass, and then by multiplying it by 100, it should put it into a percentage of change of mass. All right, so we're going to do the first one here together. Okay, so if I take a look at my data for the blue container, my final mass was 4.4 grams minus my initial mass of 6.2 grams divided by my initial mass of 4.4 grams. All right, plug it into my fancy dancy calculator and I end up with a negative 1.8 grams lost. Okay, so what does this number represent? Well, this number represents the fact that I have a decrease in change, so the mass of the potato got less. So something left the cells of the potato and we have lost mass. Okay, now if I plug in the rest of the information, I get my divided by 4.4 grams, should add that there, times 100. Okay, what is the percentage change? The percentage change comes out to a negative 29.0, I believe. Got to cheat and look, 0.03% change. Okay, all right. And you can't see my numbers. Here they are. All right, negative 29.03% change. Okay, so this is telling us that the mass of the potato then lost approximately 29% of its mass. All right, so you're going to continue to do the change of mass and the percent change for each of the following solutions. So you should end up with data that looks something similar to this. Okay, again, the percent change in mass is not necessarily going to correspond with your color changes, but it should be kind of close. You get the idea. All right, so now we got to figure out part 2, which is blue. The blue solution is what molar concentration? All right, so the question that I have for you is, what do we know already? I'm going to move my papers up here. All right. So what do we already know? Well, we already know that we have 6 different solutions, and we know that the concentration of each is this. We know that there is a 0 molar concentration. We know that there is a 0.2 molar solution. There is 0.4, 0.6, 0.8, and a 1 molar solution of glucose. All right. So we have to figure out which molar solution corresponds to which color. All right, so that means that we have to take a look at this data that we have. And if we take a look at the percent change, all right, we've kind of got numbers that are all over the place. We have some positive numbers, we have some negative numbers. We need to kind of know what is going on. All right, so there's another piece of information that we already know. And we know that the water potential of distilled water, okay, is always in an open container is always equal to 0. And we know that 0 is our highest water potential that we can possibly have. Okay? Meaning that the water really is basically, it's 100% water, so there's no solutes in there, and the water is going to be moving everywhere. It's the highest potential we have. So everything after that starts to get more and more negative. Okay, so if I take a solution, if I take a cell and put it into distilled water, we know then that the water from high to low concentration is going to move from pure water into the cell. And so it should have our greatest change in mass. Okay? Again, if I take a solution and a cell solution with a certain concentration, anything above 0, I'm going to put it into 0. It is going to move from pure water into that solution. All right, so let's go back here and we can take a look at our data that we have. And the one that is going to have the greatest change of mass should fall into that distilled water. So if I take a look at the data here, I find out that I have 2 items that had a gain in mass. Okay, we have the yellow solution gained mass of 2.94%, and the ugly solution gained a mass of 20.59%. All right, the greatest change of mass is what we're going to see with our highest water potential, and that is going to be the ugly. So, according to my data down here, I know that ugly solution is 0% molar solution. All right, as I start to add the solutes to the water solution, I increase my molarity slightly, okay, which means that I'm still going to have water moving, okay, into that solution. It's just not going to be quite as much. So if I start to take a look at these calculations, I now know that the next solution that gained water is going to be the yellow. Okay, so now here if I put my molarity or my percent changes, 20.59% next to the ugly, then I have my 9.5% change, okay, is my next highest. Now I can go through and start to organize this set of data as decreasing percent changes, okay, and each decrease of percent change should correspond to an increase in molarity of the solution. All right, so let's go ahead and do this. So my 0.4 molar solution would be my next lower, or my next highest, excuse me, change in percent. And so that is going to be my negative 14.52%. So my negative 14.52%. All right, so that corresponds with the green solution. Okay, now I can continue on where I have the rest of my data. Okay, I should have negative 23.81%. Okay, my next one then would be a negative 28.33%, and then negative 29.03%. And I can match the colors of negative 23 up with the neon color. I can do the 28, there it is, with the purple. And then I can take the negative 29, and it will be the blue solution. Okay, so I have filled in the rest of my information right here. You can see that I go from the highest percent change in the positive to the lowest percent change in the negative. And again, as we switch over to the negative, we now know that the solutes outside of the cell are now higher than what is inside, because it's going to be pulling it out. Remember that solutes suck. Okay, so my next question that I want to ask you is this. It is like, what is the potential, the water potential, of each of the potatoes? Okay, now what do we already know? Well, we know whether the cells lost water or whether they gained water. We now know what type of solution they are in. So what we are going to do is we are going to take this data and we are going to graph it. Okay, so this is going to be a slightly different graph than something that we are used to. And it's going to look something like this. Okay, so now what I have is I have my positive axis here. I have a negative axis here that is going to represent my negative change in mass. And I have my independent variable across the x-axis as usual, which are the solutions that I have chosen to place the different potatoes into. All right, so I have my molarities, again, making sure that my increments are equal. Okay, and I'm going to go through and I'm going to graph the percent change in mass as it relates to the molarity. So after I go through and I graph my sample data, I should end up with something like this. Okay, and I'm going to connect the dots as best I can. All right, keeping in mind that I've got kind of some lines of best fit going on here. What I have is two sets of data. I've got a zucchini core that was stuck into some different various solutions of salt, of sugar water, and then I also have potatoes. So maybe one of yours looks like this. All right, after I connect the dots, all right, again, what do we know? Well, we know that the change in mass, okay, the change in mass is going to be equal, or there will be no change in an isotonic solution. Okay, so once I have my information plotted, okay, that I go through and I say, all right, well, where do I have zero change in mass? Well, zero change in mass over here is right here on the x-axis. There it is. Okay, and so if I follow it along and I want to know what is the molar concentration inside the potato, I can go through and find out, because at an isotonic solution where the inside of the potato is equal to the outside of potato, there should be no change in mass. So coming through here on my data table on the potato line, if I take a look where the line of our data crosses the x-axis at 0% change, I will see that my molarity of the potato is going to be between 0.2 and 0.4. Now, let's see if I can see the lines underneath here so I can get a better, there we go, indication of where I am lying. Okay, it is not quite to the next box over. Okay, so if this is 0.2 and this is 0.4, we know halfway in between is probably about 0.1, and halfway in between that is about 0.15. So I'm going to say that my change in mass is about a sorry, I went the wrong direction. That would be 3. That would be 0.25. I'm going to say it's about 2.3 molar solution. Okay, again, I can do the same thing for the zucchini core, where again, at the equal change, or at no change in mass, should be an isotonic solution. So it should be right here on this x-axis. Okay, let's see, where am I? Right here. Okay, I have a line here. I have a line here. So again, it's not quite 0.4. I have between 0.2 and 0.4. Halfway is right here at 0.3. Okay, and halfway is about 0.15. So I'd say it's probably about 0.3. Let's see, probably 1.5, right? Molar solution. Okay, all right. And so that is how you figure out an unknown water potential based on the solutions that they are in. And I hope that you understand this. Please feel free to rewind and go over the talk as much as you need. All right, this is take 1.